Welcome to my channel Ganit Matrix. Here we are going to discuss some more problems on Jacobian and functional dependence. Now I have published one video on Jacobian where I have discussed the concept of Jacobian and few problems on it. So for your convenience, I am giving the link in the description so you can watch and share with your friends. Now coming to the problem, determine whether u equal to sin x plus sin y and v equal to sin of x plus y are functionally dependent. So when do you say that two functions, since u and v are functions of x, y, we say that u and v are functionally dependent if their Jacobian is 0, right? The Jacobian dou of uv by dou of xy equal to 0. So first we will calculate the Jacobian. So this equal to dou u by dou x, dou u by dou y, right? U with respect to x, u with respect to y. Next, second row, v with respect to x, v with respect to y. Now we find the partial derivatives. First row, since u equal to sin x plus sin y, same thing, with respect to x we treat y as constant and with respect to y x as constant. So dou u by dou x equal to differentiation of sin x cos x, and with respect to x y constant, so here the differentiation 0. Similarly with respect to y, x constant, so here the differentiation 0. Dou by dou y of sin y is cos y. Since v equal to sin of x plus y, right, and dou v by dou x equal to cos of x plus y. Dou v by dou y cos of x plus y. Substituting this first order partial derivatives in the Jacobian, the 2 by 2 determinant, we'll get this, right? So expand this determinant, AD minus BC, right? So cos x into cos of x plus y minus cos y into cos of x plus y. Taking cos of x plus y common, so this is cos of x plus y into cos x minus cos. And this means our Jacobian is not identically 0. That means the Jacobian is not identically 0. See here, suppose if we take x equal to 0 and y equal to pi by 3, so what will get? J equal to cos pi by 3 into 1 minus 1 by 2. So this equal to 1 by 2 into 1 by 2, 1 by 4, which is not equal to 0. So we choose arbitrary x and y values. Since the Jacobian is not identically 0, therefore the functions u equal to sin x plus sin y and v equal to sin of x plus y are functionally independent. That means this is not functionally dependent. Coming to the next problem, since if u equal to x square minus 2y, v equal to x plus y plus z, and w equal to x minus 2y plus 3z, find dou of uvw by dou of xyz, right? Jacobian of 3 variables. So here dou of uvw by dou of xyz. So for defining this Jacobian, u must be a function of xyz, right? And v must be a function of xyz, and w must be a function of xyz, right? So here, therefore the Jacobian is defined. So this equal to same thing, u with respect to x, u with respect to y, u with respect to z. Similarly second row, v with respect to x, v with respect to y, v with respect to z. Third row, w with respect to x, w with respect to y, w with respect to z. So first we calculate the partial derivatives of u with respect to x, y, z. Same thing, dou u by dou x, 2x, since with respect to x, y constant, so here differentiation 0, differentiation of x by 2x. Similarly, dou u by dou y, with respect to y, x term constant, so here differentiation 0, differentiation of minus 2 by minus 2. And dou u by dou z means with respect to z, x, y constants, therefore dou u by dou z is 0. Same thing, v equal to x plus y plus z, therefore dou v by dou x is 1, right? Dou v by dou y 1, dou v by dou z 1. Same thing, right? So w equal to x minus 2y plus 3z. So with respect to x, y and z constant, so here the differentiations are 0, differentiation of x only 1. So dou w by dou y. So with respect to y, x and z term is constant, so the differentiations are 0, differentiation of minus 2 by minus 2. dou w by dou z. So with respect to z, xy terms constants, dou w by dou z equal to 3. So substitute these all first order partial derivatives in the given Jacobian. We will get 2x minus 2 0 and this. So we expand this determinant by first row because the first row contains 1 0. So 2x into remove first row and first column. So this is 1 1 minus 2 3 minus second row, second 1 2 element minus 2 into, means remove first row and second column, 1 1 1 3 plus 0 into this. So 2x into, so AD minus BC, 3 minus of minus 2 plus 2 into 3 minus 1 which is 2x into 3 plus 2 plus 2 into 2, which is 10x plus 4. Now coming to the next problem, if x equal to rho sin phi cos theta, y equal to rho sin phi sin theta, and z equal to rho cos phi. So these are called spherical polar coordinates. Then find dou of xyz with respect to rho theta phi. Same thing. So first we calculate the partial derivative with respect to rho. So first we will calculate x with respect to rho, x with respect to pi, x with respect to theta. So dou x by dou rho equal to, so with respect to rho, phi theta term constant, so we write sin phi cos theta as it is, differentiation of rho 1. So dou y by dou rho, same thing. So with respect to rho, same sin phi sin theta are constants, differentiation of rho 1. Dou z by dou rho, which is cos pi. So calculate the other partial derivatives with respect to pi. Dou x by dou pi is rho cos pi cos theta. Dou y by dou phi is rho cos pi sin theta. Dou z by dou rho minus rho sin phi. So after calculating, so this is the partial derivatives of x with x and y z with respect to theta. So we get this. So expand this by third row. Expand this by third row because third row contains 0. So cos pi into remove third row first column plus minus of minus plus rho sin pi, remove third row and second column, and second column. So we will get this. So for the first determinant, right, so rho square, so first we are expanding the first determinant, this one. So rho cos phi cos theta into rho sin phi cos theta, which is rho square cos phi sin phi cos square theta plus minus of minus plus rho square cos phi sin square theta. This is rho square cos phi sin phi into taking rho square cos phi sin phi common, which is cos square theta plus sin square theta. So this is the trigonometric identity, cos square theta plus sin square theta is 1. So this is rho square cos phi sin phi. So this is the first determinant value. Same thing, second determinant, if we expand that, we will get rho sin square phi cos square theta plus rho sin square phi sin square theta. Right? So this is same thing, rho sin square phi common, cos square theta plus sin square theta 1. Therefore, our Jacobian becomes, since substitute this first determinant and second determinant, so here in J, we will get cos phi into rho square cos phi sin phi plus rho sin phi into rho sin square phi. Taking, so this is rho square cos phi into cos phi cos square phi sin phi plus rho square sin cube phi. Taking rho square sin phi common, cos square phi plus sin phi sin square phi. So cos square phi plus sin square phi 1. So this is rho square sin phi. So therefore this is rho square sin phi. Thank you.